Hello everyone, welcome to Dawn of a New Era. You'll have to forgive my puns and jokes. There's a few more, not many, don't worry. So I'm Phil Nash. You may have seen me before this week already, but if not, you may know that I work at JetBrains. I'm developer advocate for the C++ tools. So if you haven't done so already, do come and see us on the JetBrains booth over the other side. We're all very friendly. I'm also the author of Catch, or Catch 2, the test framework. So if you haven't tried that, do give that a try. But today I'm talking about error handling. Hopefully that's obvious from the title. And I think the animation has finished now. This photo, by the way, I took this. We had a winter trip with JetBrains to the Austrian Alps last December. This is the view from the hotel room. So it was quite nice to include that on my title slide. But before we really get started with the meat of the talk, I'm going to go into a little bit of history, because we're going to be talking about this. So this is not history, this is the future. This is a new proposal from Herb Sutter with the input of lots of other people. We're going to dig much more into this as we go through, but it's about exceptions, a new type of exceptions. But I said a bit of history, because this is not the first talk that I've done on this subject. Last year I was doing this one. Optional is not a failure, so yes, another pun in the title. And I did this a few times. But what's interesting about that talk is when I first proposed it, I hadn't seen that proposal, P0709, that I just showed you. When I put this talk together, I was putting into it my own thoughts about error handling and exceptions based on what I'd seen in other languages and sort of reading the tea leaves and seeing what direction we're going in, how close we are to it, and what we can do next. And even more interesting, this is not even the first talk I gave with this title. Before that, I gave this one, same title, Optional is not a failure, but it was a mobile development conference, and I was talking about Swift. And that's significant because this is what got me thinking about these ideas in the first place. The claim I made in this talk was that Swift has what I consider to be one of, if not the best, error handling approaches in any language. And that was quite a bold claim. And in fact, the last time I gave this talk at another Swift conference, I made that same statement, and I saw like about half the audience just sort of nodding sagely, all agreeing with me. And what was interesting is I saw a lot of the same things going on in C++. We're sort of almost there, but not quite. And I wanted to talk about how a few little language changes we could get there as well in C++. And then before I actually gave the first version of that talk in C++, I read Herb's proposal and realized I was not the only one thinking about these things, and maybe this will become a reality after all. But before we get to that, I want to go back to a little bit more history, because I've been thinking about alternatives to exceptions for a while, particularly since I started looking at what we call exploding return types. Who here has heard of or used exploding return types? Not many. No, it's quite an old idea, and there's reasons why we don't do this anymore. But I first heard about that in this talk, I think, from 2007. No videos from back then, but Andrei Alexandrescu gave the talk, Choose Your Poison, Exceptions or Error Codes. The idea being that, well, there are trade-offs between the two. And this is a big part of my previous talk as well, weighing up all the trade-offs between different types of error handling. And we want to make different choices in different situations, and baking that in at the implementation site is not always the best choice. And he proposed this template, which he called likely T, and had a really interesting property. And that is, it can act like an error code that you can check to see whether it has an error or not, and otherwise get the value out. Or if it's not an error, get the value out. But if you don't check, and here's where the exploding part comes in, the destructor throws. So it keeps track of whether you checked the error status or not. And if you don't, the destructor will throw. So not something you want to happen, but it lets you know that you haven't checked things. You can't ignore it. Now, we have better ways to do this now. But back then, that was quite a revelation, and I started using something like this on my own code. And actually, this is not the first use of exploding return types. I found this post on complang C++ moderated from the year 2000. You can see the date up there, possibly. I like the way he opens. Out of intellectual curiosity, I wrote the following class. Yeah, right. But there again, you can see in the destructor, if you haven't checked the return code, it throws an exception. And in fact, in that thread, I found references to earlier work from Lisa Lippincott and James Cans. They've both been doing this sort of thing before. And in fact, Lisa actually weighed in on the thread, and I like what she says here. Let's not repeat the mistakes of the past. Model the copy construction and assignment on the current auto pointer, not the old broken one. Simpler times, eh? But anyway, that's all an aside. Coming back to Andre's type. After 2007, the next mention I saw of it was in 2012. This talk is C++ and beyond. Systematic error handling in C++. Now, what had happened between 2007 and 2012, of course, was we now have C++ 11. And one of the things that C++ 11 introduced was no except, and in particular, no except by default on destructors. So, exploding return types had a bit of a problem now. So he didn't have a throwing destructor anymore, and he'd evolved the type a bit more. But same principle, it's a type that included either the value you wanted or an error and a way to check it. We still have, in this get method, I don't know if you can read that, it's not a great slide. If you haven't checked the error, so it is an error, it still throws an exception. Exceptions are still involved. It just pushes the use of them to the call site where you can make a judgment. Now this type now had a new name, which was expected. And we now have a standard proposal for stood expected, based on those same ideas. It's actually been going through for a couple of years now. I think it's still in the standardization queue, so it's probably not going to make it into 20 as far as I know, but I haven't been keeping track just recently. So, yeah, a lot of people are interested in what this can do. And of course, this idea is not new to C++. It's been around for quite a while. And just from a few languages I'm familiar with, here are some of the equivalent types. So Haskell has the either monad. You may have heard of the either monad. It's basically the same thing. All of the other languages here have something called result, but they're slight different variations on how that works, what language support you have. Rust has particularly good language support for this, particularly with a very lightweight monadic binding approach. We'll come back to monads a little bit later, don't worry. Swift is interesting. We mentioned the Swift already. I said earlier that I thought that Swift had one of the most advanced error handling approaches of any language, and yet it only got the result type. This is Swift 5, just about a month ago that was released. So how come? Well, this is a stepping stone to where I think we should actually be getting to. Swift sort of leapfrogged ahead of this, and only just sort of came back recently to fill the gap, because it turns out that result can still be useful for some things. So that's interesting as well. They now have that. So in C++, we're getting stood expected, hopefully. Should serve the same role. How does that actually work? What does it actually give us? Let's have a look at it in practice. So here's a really simple example with a function for converting a string into an integer, using string view because we want to be nice and modern. And notice in particular the return type. By the way, I always prefer trailing return types. Return type is stood expected of int or, in this case I've used stood domain error. Could be any type there. We're not limited. Previous times I've used strings, for example. And the point is, what we actually want, what we expect this to return is an integer. But in the error case, we can return something else. So at the bottom, not highlighted, you can just see it returning the integer. That works. But in the unexpected case, we return a stood make unexpected, because that disambiguates the constructor, of our error type. And I'm just building up the domain error there. Nothing particularly special about that. There's nothing particularly special about the rest of the implementation either. It's a pretty boring string stream. You can write this much more efficiently, just for the purpose of the illustration. So that's how you would write a function to return a should expected. But how would you call it? Put some more code up. So here we're calling our parseInt and capturing the result, and then we need to test it. Could do this all in one line, actually, but actually there's something we'll do in a minute that requires it to be separate, so I'll leave it there. So we can test the result just like we would with a pointer or a std optional, just using the explicit conversion to bool, I should say. And if it has the value you wanted, we can dereference it again like a pointer or like std optional to get the result out. But unlike optional, in the error case, we can call .error on it to get the error type. And because this happens to be an exception type, we can call .what on it. Again, if it's any other type, we can get that out as well. So pretty simple stuff, really. Nice and easy to use, but there is a bit of a problem with it, which I can highlight here. So the yellow highlighted code is the happy path, and it's dominated by the error path, by the error handling. In just a small example, most of the code, or more than half of the code, is error handling. And that's not so nice. And it doesn't scale very well either. In fact, let's add some more functions and try to compose them together and see what that gives us. So now we've got another function, divide, takes two integers, and again returns a std expected of int and domain error. And all we're doing here is dividing one by the other, but we're just checking for divide by 0 and returning an unexpected result in that case. Again, really simple stuff, just so we can focus on the mechanics here. And just for fun, we'll throw in one more function. This one doesn't have any error states. It's just going to add 1 to an integer. We'll ignore overflow for now. So no unexpecteds, no std expected here. All right, so how might we compose these three functions together? Well, this is how you typically might do it. So we've got to capture the first result, test whether it had an error or not. If it didn't, then we can dereference it and pass it on to the second function, but capture a second result, test that, dereference that, pass it on to the third one, and then, of course, capture all the error cases as well. Lots of heavy nesting. The happy path, if I can get that to work, ends up right in the middle of all that nesting there. That's where you actually want the code to end up. It's not particularly nice. Now, you might think, well, we could make this a bit nicer if we use early returns rather than all this heavy nesting. Let's have a look at what that looks like. It's a little bit better, not much. And we can't always use early returns, so I'm not sure that's that much of an improvement. And bear in mind, this is sort of the leading edge of error handling in C++. It's not even in the standard yet. And yet, it's causing us these problems already. So what can we do about this? We mentioned earlier that lots of other languages have a similar approach, including, of course, Haskell. If Haskell has a solution, it's got to involve monads. So I did say that we'll come back to monads. Don't worry, we're not going to get into the theoretical side of it. Just going to talk about the operations that it's going to give us. So there's another proposal. Monadic operations for std optional. Now we're talking about std expected, but the same thing applies. So this proposal is from Simon Brand, and he wrote a blog post a couple of years ago now, proposing the same ideas that led on to this proposal. In the blog post, he actually talked about optional and expected, but I think it's concentrated on optional here, just so we can get that through quickly, because we don't actually have expected yet. But the idea is we'll get exactly the same operations on std expected, if that goes through. So we can extrapolate from this. So what does it give us? Well, zooming in a bit on the abstract. Oops, too far. It says, I propose adding transform and then and or else member functions to std optional or std expected to support this monadic style of programming. Okay, so three functions, methods rather, mentioned. And if you have used functional programming or know these terms, you might know that transform is the same as map we might normally use, and then translates to bind. And the or else, since we're talking about error handling here, you might think of that as like a catch. It's where you handle the error case. at least in the stood expected example. So these are the three methods. What do they really mean, though? Well, let's go back to our example and see how we can use that. So this is where we got to with our nesting. This is what happens when we use those operations. Before we look into how that works, I think you'll agree it's a lot less code. And I think it's a lot simpler. It's a bit verbose because of the lambda syntax. But there's no moving parts here. That's all hidden from you now. We just have, in fact, if I show you, the ratios are much better. The happy path now dominates, only slightly. There's still a fair bit of boilerplate, again, coming from the lambda syntax mostly. But what we're actually doing is, if you need to compose two functions that return errors but take raw values, return possible errors, take raw values, use and then. If you want to compose it with a function that takes a raw value and returns a raw value, use transform. That's it. That's what the monadic operations are, at least in this case. So you can scale this. The flow through here is actually much simpler as well. It comes in the top, carries on through. In the first case, it sort of winds its way out. So this is not bad. Certainly better than we had before. But, it's still not great either. I think we're still not quite there yet. In some languages, the syntax here is nice enough that actually that's good enough. But for C++, we're still bogged down by all this boilerplate. So let's have a look at what we're competing against. Because this is what it looks like if you use exceptions today. This in terms of syntax, this is our baseline, really. Let's just do that again. Right. That's the best we could do with currently proposed and currently not even proposed features. This is what we can do today with exceptions. So what's the problem with exceptions? Well, that's what I went into a lot in my previous talk, and I'm sure most of you are aware of most of the problems with exceptions, but really we're talking about performance is usually the number one reason for most people, particularly or at least on the error path. Performance can be like 1 or 2 orders of magnitude slower in the case of an exception. But maybe even more important than performance for whole groups of domains is the determinism, because it's not predictable how much time or space exceptions are going to take. And a lot of it's implementation detail or even just runtime, because exceptions as we have them today rely on dynamic allocation, polymorphism, RTTI to do the catches. It's all the things that violate the zero-cost abstractions principle of C++. So that's quite a cost. But there's also one more thing. And it's maybe not quite so obvious here, but yes, this is a lot less code, maybe even too little code. We now don't actually see any error flow at all unless we look into the implementation, which you can't quite see at the top there. There's nothing in the signatures to indicate the functions may return an error or yield an error, and there's nothing in the call that indicates that errors may occur here. You just have to know. It's all implicit. So yeah, that cleans up the syntax a lot, but a bit too much, I think. So could we solve all of these problems? Could we get something that has all of the performance characteristics of the stood expected approach, but with none of the downsides, and also the explicit nature of knowing what functions can throw and what expressions may throw, but without all the extra boilerplate? Can we have it all? Well, this is what the proposal, P0709, will give us in this case. So, in case you missed it, here's the difference. Exceptions as we had them today. At the call site, we just add the try keyword. In fact, we'll zoom in a bit, just make that a bit clearer, see the function as well. So we have a throws keyword at the end of the function signature. So you have to explicitly mark a function as something that may throw. But that's it. We don't specify types. So this is actually still less syntax than the stood expected way, but it gives us the same ability to reason about our functions in terms of the error handling. Now, when you have a function that's marked throws, then when you see the throw keyword in that function, that now has a slightly different meaning. Now we're no longer throwing a dynamic type that has to be allocated on the heap and then decoded at the other end using RTTI, but now we're throwing a value, a simple value type. And actually, we're going to come on to digging a lot more into that value type in a moment. But for now, just bear in mind, this is a simple value type. It's as if the compiler can rewrite this to the example that we saw before with stood expected, but with a much lighter syntax. And then, of course, at the call site, we just have that try keyword there. So it's a try keyword rather than a try block. It's a different thing, and it just means that this is an expression that may throw. You can call something that has the throws keyword. And that's checked by the compiler. So if you miss that, the compiler will tell you. And you might think, well, why is it necessary in the first place then? And strictly speaking, it's not. This is just to make things more human readable, to make the control flow due to exceptions or errors visible in the code, but without bogging it down with all that extra boilerplate. In a way, it's a bit of a compromise, and some people would actually prefer not to have this. I'm definitely in the camp that I think we need this. We need it to make it easier to reason about our code. Strictly speaking, it's not necessary. Let's put a little bit more context around this. So we've got that code at the call site. Let's put it in a function. So if you don't catch one of these exceptions, then the function that it's in must also be throws, because it can propagate out. Makes sense if you think about it. So again, checked by the compiler, so it will tell you if you haven't done this. Just to summarize, these are the new or altered keywords. So we have throws on functions with the try keyword, and then throw within a throws function up there now has a slightly different meaning. So only a very small change to the language, really, but can make quite a profound difference. Just to complete this, we can use Trycatch, as you would expect. These have more or less the same meanings, but if you catch a value and the function throws a value, there's no RTTI. We just catch the value. Again, we'll have a look at exactly what that error type is a little bit later. What I want to emphasize, though, apart from the fact that this is a very small change to the language, very small amount of syntax that improves things just on its own, is that this is effectively, not absolutely, but effectively isomorphic to the example that we saw earlier with stood expected. When you see throws, you can mentally map that to stood expected of the return type, which might be void, and stood error. So the stood error is effectively hard-coded. When you see throws of that type, it's like you're doing a stood make unexpected of that type, that value, sorry. And the try keyword, well, some people complain about those 3 characters, but this is what they're doing for us. They're standing in for, even in our simplest case, our most succinct case with the monadic operations, they're standing in for all of that boilerplate for us. I think that's a pretty good bargain, if you ask me. That's right, yes. So the question was, so is it like you're saying it's going to wrap your return type in stood expected? It's like that. And I want to emphasize the fact that it's as if you're doing that. And in fact, maybe stood expected is not the right type because stood expected still has exceptions in them. It's actually more like boost outcome. But we won't get into that. I'm saying it's like that because also this works for constructors and operators, anywhere that you can't actually return anything or return the error type. This works the same way that exceptions does as well. But if you think of it this way, then it will have effectively the same characteristics in terms of performance, determinism, and so on. In fact, because we are more clearly communicating our intent to the compiler now, the compiler can actually optimize it even more, potentially. So it could actually even be better performing than the stood expected case. And in particular, that the choice of whether you have an error type or a return value could be stored in an unused bit in one of the return registers. So you get that for free. And then at the call site, the test for it, if you think of it as an if statement, well, with the appropriate use of likely and unlikely, you can probably get branch prediction in your favor to optimize that away as well. So we call this zero cost abstraction. So it may even be less than zero cost abstraction compared to what we would do by hand. So that's really the summary of what I did in my previous talk. So what I want to do now is drill down more into this type, stood error, because I didn't go into this at all in my previous talk. By the way, if you want to watch the previous talk, you haven't seen it already, there will be a link to some references at the end with all of the proposals and some links to those talks. So I've summarized it for now. But what is this type? What does it actually give us? Why is it so important? So there's another proposal that defines this type, P1028, status code and standard error object, for P0709. So right in the title it's saying this is a supporting proposal for the so-called static exceptions proposal. Don't let that fool you though. This proposal actually stands on its own right and is very worthwhile even without static exceptions for reasons that will hopefully become obvious as we go through. So let's have a look at what this proposal is all about. So right at the start of the abstract, it says, it's a proposal for the replacement in new code of the system header, system error, with a substantially refactored and lighter weight design, which meets modern C++ design and implementation. So who's familiar with the system error header? Very few hands, which is quite normal. It's been in the standards since C++ 11. It was actually based on what's been in Boost for years before that, used extensively in Boost file system and Boost ASIO. The standard version is in standard file system and the networking TS. So it's a very important and actually quite widely used header and the type in there, and most people don't know about it, which is really interesting. And I would say people should know about this. You should go and read up on it, maybe make more use of it, except that there's a few problems with it, which is what this proposal tries to fix. So let's dig into it a bit more. So we're looking at stood error. This is the definition. It's actually a type def we're using for this type. Arid status code, erased system code value type. Not very helpful. We're going to unwrap this in a minute. But to do that, let's go back in time again to the formation of C++ 11. This is the thing it's replacing. This is what we'll get from the system error header. Stood error code. So it's like subtle differences in naming here. It can be hard to keep track of which one's which. The old one is, that we have now, stood error code. The new one we're talking about in the proposal is just stood error. So we've got the simpler name. That's good. But what was stood error code? We need to understand this to really understand stood error. Here's a sort of a sketch of what it is. There's obviously a bit more to it, but this is the important part. We've got two members, an integer value and this error category pointer, which happens to be const. And that's it, really. Quite a simple, unassuming type. It's got a few methods that are significant. There's a couple of accessors, so we can get the value, we can get the error category by reference, but it's basically an accessor. We can also get a message out of it, and we can do a conversion to bool. That's interesting. How do we get the message out of it if we just have an integer and a pointer? There must be something in that error category. So let's have a look at what error category actually is. That seems to be where the meat is. An error category you can think of as a domain for errors. And that's an interesting term, actually. Everyone describes error category as being a domain of errors. Why didn't they call it error domain? I don't know. So it's a domain of errors. And within that domain, you'll define enums for all of the types of errors in that domain. So we have this domain for POSIX errors called ERC, which is actually defined in the standard. So all the POSIX errors are there, so you've got the POSIX values on the right. But you can create your own domains, like the one on the right, my errors. Put anything you like in there, because you're creating your own error category. So if you do that, you have to create an error category class, so something derived from error category, and it has to implement a load of methods. Here's some of the important ones. We've got a couple of methods called equivalent, and then we've got that message. So this is where the message comes in. So on stood error code, when you call message, it forwards on to message on the error category, and will pass in that integer. So it's actually forwarding the responsibility onto the error category to decide how it's going to pull that message out. So it effectively going to convert that enum into a string at that point. However you see fit to do so. Could be a lookup table, could be a big switch statement, could be a conversion, it's up to you. What about these equivalent methods though? What are they all about? Well, here's the really crafty thing about stood error code and these error categories. There's this idea that within these domains, these different domains, certain errors are equivalent to each other. If you're working in the POSIX domain and you've got things to do with bad files, or you might be working in another domain that also has a concept of a bad file. Well, those two things should be equivalent. And there might not be one-to-one mappings. You might have multiple codes on one side mapping to multiple codes on the other side. These equivalent methods let you do that. They let you say that, well, for this error code, we're equivalent to this other error code. But I don't know if you can see that there at the top. The actual type being passed in here is error condition. We haven't talked about that yet. What's error condition? This is something that trips up a lot of people, and it's, I think, an unnecessary complexity in this design. Error condition is basically like error code, but it's a separate type just so we can overload on it. So we can say, are we comparing against an error condition, in which case it's an equivalence comparison, or are we comparing against another error code, in which case we do an exact match? And it has to be the same category. It's a subtle distinction. And a lot of people that have even been doing this for a long time get tripped up on this, so that's one of the problems. There's an example of the equivalence. All right, so going back to those methods, so we know where message comes from now. What about that Boolean operator? That seems to be a simple thing. You would think, yeah, that's just going to be whatever maps to an error or non-error in your domain. That would be really useful if that was the case. Unfortunately, it's not. All this does is just check whether the error code, that integer, is 0 or not, which may or may not imply a non-error. So it seems they missed an opportunity there. So it's almost completely useless, unfortunately, even though it's tantalizingly close. So just to summarize, and I actually add a few more. These are... In some domains, so the question was, isn't that the same thing? Doesn't having a 0 mean not an error? It depends on the domain. It depends on how you define your enum. If you define your enum so that 0 is non-error and everything else is an error, yes, and it's quite common, but by no means ubiquitous. So unless you know exactly which domain you're dealing with, or category, should I say, you can't rely on it. So here's a summary of the problems with error code. We looked at some of them. Because of that message, the way that message thing works, and because when you're comparing error categories, it compares on the pointer value. Remember, we're holding the category by pointer, and that's its identity. The implication is that those error categories must be implemented as singletons. They have to have a stable address in your process. So just having the singletons alone can be a problem, but there's a very real problem when you have header-only libraries within dynamic libraries. Because each dynamic library, instantiating a singleton in a header, gets a different address. And that breaks this. So it seems like a really small edge case, but it does actually bite people in practice. Depends on std string. Doesn't seem like a big problem. But yeah, message returns a std string. Therefore, in order to use std error code, you also depend on std string. And everyone uses std string, don't they? Why is that a problem? Well, consider the people that are more likely to be using error code instead of exceptions. They're the type of people that don't want to include things like locales and IO streams and exceptions. All included if you include std string. So that can be a problem for some people as well. We mentioned that the ball conversion is not reliable because it depends on the category. We mentioned about the error condition type being separate and how that's a really subtle complexity. Almost none of it is const expr, which is not surprising given that it came in C++ 11 when const expr was very limited and was actually based on a design that predated that. Much more of it could be const expr. And the error code, although it's defined as enums, it's actually stored as an integer. So that's the limitation as well. And so the little thing, but yeah, in order to explain what a category is, you say it's a type of domain. Why didn't they just call it domain? So a bit of a naming issue, but a minor point, really. Okay, so this is the equivalent type in the new proposal. Status code. So remember, we're actually working up to this type def. This is one of the components, status code. This is the equivalent of std error code. So it looks a little bit familiar. It's got status code domain. As we said, the error category of the type of domain. Well, here it's actually called a domain, playing the same role, still a pointer, except that the identity of this is no longer its pointer value. There's another way of doing that, so that addresses that problem. And then we have the value, which is not just an integer, it's now a template type. We'll make it concrete in a minute, but it means it doesn't limit the design overall. And if we bring back that using statement that we saw earlier, we notice we're actually not quite there yet, because it's not status code that we have, it's Arid status code. It's actually a really simple explanation for that. Because with error code, we only ever want to deal with errors. So Arid status code is basically status code, but will never represent an error. And this is enforced in the constructor. So if you try to construct an Arid status code with an error value, throws an exception. Oh no, sorry, terminates, I think. In any case, you catch it quite quickly. Just don't do that. And for our purposes, that will never happen because that's going to be constructed behind the scene. But point is, if you get an Arid status code, you can guarantee that's never an error, regardless of what's in the domain. So that's convenient. We don't have to worry about that. In fact, that whole problem with the Boolean operator, which is solved here anyway, goes away. All right. So that's all the status code is. What about this erased system code value type? So you might be thinking that erased is some sort of type erasure template, and it is. What it is its template parameter is the type whose size is going to be the storage of the erased type. So anything that fits in the same size of system code value type can be stored in one of these things. Seems unnecessarily complex for this sort of thing, but actually there are real use cases for this where you want to use different things. In fact, we're going to look at one of them. What it means is that in practice, this is what that system code expands to. So it's as if you have written a class error that has, with a status code domain and an int pointer t, because that's what sorry, if we go back, system code value type expands to. That is never a success code. So very similar to what we had before, but with more guarantees, and a little bit more flexibility. Because it's an int pointer t rather than an int, that means it's always going to be big enough to hold a pointer as well.
So
yes?
With an L, you don't need the bool, because it's always an L. You can't hold something with an L.
Yes, your point was we don't need the Boolean operator anymore because we know it's always an error. And yes, in our case, because we're using Arid status code, that's true. The more general design, because if we go back, because that's the template, sorry, where were we? This one. We could actually use status code outside of this for different reasons. So it's a more general design. But for our purposes, we're using this type def, and therefore we don't have to worry about the error code, the non-error values. We don't need to touch that Boolean operator. But it's fixed anyway. Nice to know. So, again, just to summarize and add a few more, these are the things that stood error code fixes. So domains are actually called domains, hooray. The identity of domain is based on a randomly generated uint64 ID, generated at design time, not at runtime, which means it's always going to be stable. And no, there's no problem with clashes. You can look into that if you like. So there's no, because there's no pointer comparisons, we don't have to worry about issues with singletons. In fact, there's no need for singletons in this. The value type, in general, can be any small, and here's an important point which I'm going to expand on, any small trivially copyable or movable type. We'll expand on that in a minute. There's no string dependency, at least as currently proposed. Remember, that was one of the issues before. What this proposal does is it actually defines its own string ref type. I don't know whether that's going to be seen as too much, but it does solve the issue. It's mostly context-extra, because it's been designed in context of C++11 and beyond. There's no Boolean conversion necessary, as you say, and the comparison is always equivalence now, which means we don't need that separate type. We don't need something like error condition. There's only stood error code. If you can compare two stood error codes, it's an equivalence comparison, and so two different values may compare the same. So it's not a regular type. In this case, this is what you want, because you only ever really want to compare equivalent values. If you really, really need to, you can actually just pull out, with the accessors, you can just pull out the error domain and the code and compare them independently, but no one ever does. So that solves all of the problems with stood error code in a much nicer way. But what about this trivially copyable and movable thing? Well, the first thing to note is that this type, with the pointer and an int pointer t, we know exactly what the size is now. We know that it will fit in 2 CPU registers. And if moving this type is the equivalent of mem copying its bits, then we can say that it is trivially relocatable. And that's significant because it means that we don't have to invoke move constructors and destructors or anything. We can just copy bits around. Because they're registers, it means we can just copy registers. That's really significant when we talk about using this on the return channel for error handling. All we're doing is just copying 2 registers. That's it. But that means we need a way to communicate to the compiler that this is indeed trivially relocatable. We don't currently have a way in the language to say that. We can say it's trivially copyable, but if we want to put a type in storage, because remember storage, it's actually an array's type. We don't actually know what's in there. We don't know whether that is trivially relocatable or not. If we put a pointer in there, like a unique pointer, move-only type, then trivially copyable doesn't help us. So that's another proposal, another supporting proposal. P1029, move relocates. In fact, there's another one as well. This is an alternate one, P1144, object relocation in terms of move plus destroy. So what do these two proposals give us? Let's just compare them side by side. I think we'll show up the differences much more readily. So the first one, move relocates, only defines an attribute to indicate that move is trivial, i.e. it can be a memcopy, which is all we need in order to support static exceptions efficiently. Whereas P1144 optionally provides the equivalent attribute, so that's not even a mandatory part of the proposal. But it also defines a load of other things. Has a detection trait, so you can tell whether something is at compile time, is trivially movable. More importantly, and perhaps more controversially, it can actually reset the moved from state, again using memcopy. The idea being default construct one of these types. If you can memcopy its bits into something that previously had a value, that effectively resets it. This is the so-called destructive move. If you want to know more about it, read the paper. We're not going to dig into it more than that. But you probably have heard that destructive move has a long and tortuous history, keeps getting rejected. And that's why P1029 exists. It's much less ambitious. So if we currently P1144 is going through standardization, looking good so far, but if it doesn't make it, we can fall back on P1029 and still got what we need for the purposes of std error code. Sorry, std error. Okay, so hopefully you now have a better idea of what std error is and why it's so useful for this. It can hold everything we need it to hold. It can hold error codes in different domains like std error code did, but fixing all of those problems. It can also hold pointers. I mentioned that in passing, but now we look at it in the context of exceptions. That means that although we are throwing values here in a very efficient way, we can still put exception types in there if we want by pointer. So we can opt in to that dynamic allocation if we really need it, and this will still all work. Which also means it can interoperate with the so-called dynamic exceptions, legacy exceptions. So that's really nice. It does all of that. And in fact, I haven't even shown you how you can pull out values yet, but it's a very versatile but simple type. It's really nice. So let's summarize by looking at all the proposals we've been talking about. So the main one, P0709, zero overhead, deterministic exceptions, throwing values, also known as static exceptions. I think even Herb has started calling it that now because everyone's calling it that. It can be a bit misleading to call it static exceptions because the exceptions themselves are not static. They're just not dynamically allocated, that's the key. Throwing values is actually the main point. But that's supported by P1028, the basically std error, although it says status code because that's the component type. And then either P1029 move relocates or P1144 object relocation in terms of move plus destroy. We looked at those two last. But we also have std expected. That's not actually part of this, but it's related. And P0798 monadic operations for std optional, possibly joined later by the equivalent for std expected. We've mentioned those as well. And then honorable mention for this one. I went into this a little bit more in the previous talk. Support for contracts. Seems like it's nothing to do with this, but actually the reason this is significant, and if you haven't looked at contracts yet, you should, because this is going to change the way we do a lot of things, which is sort of the point here. A lot of things that we currently use exceptions for actually should be contracts. And in fact, we have in the standard right now std logic error and a few types derived from it. And it's been said that std logic error is itself a logic error. If it's a logic error, we shouldn't be recovering from that. We should, by default at least, be terminating. And obviously there are some exceptions to that, if you pardon the pun. But If we can define our contracts using contracts instead of exceptions, that takes out a whole class of things that we currently need exceptions for. In fact, most of the standard library's use of exceptions should actually be contracts. And then what's left is mostly bad alloc. And we haven't really talked about that yet. Again, I went into this more in the previous talk, but there are proposals to change the behavior of heap exhaustion so that by default, if new cannot allocate memory, rather than throwing bad alloc, it terminates. That sounds more controversial, but actually getting a lot of support. And there's lots of reasons for that, which I won't go into now. Again, talked about it a bit more in my previous talk and in other places. The point is, if we make that change as well, that means there's only like 1 or 2 places in the standard, like very few, that actually still would throw exceptions. Things like, out of range when you're accessing a vector using .get, for example. Very few places actually use exceptions. We could then change those, potentially, to using static exceptions. And one of the concerns people have is adding these throws keywords and the try keyword everywhere. It's just going to clutter up the code with all these noise keywords. But actually, if you get rid of most of the need for them, the few that are left, then it becomes much clearer what the control flow is, and that you need to pay attention to this. So that's why contracts are important as well. They're all the proposals we talked about, one way or another. And that is the end of my presentation this morning. Thank you very much. And we'll take questions, but I should also mention, I said that all the references will be at the end, so there's the link on my website, levelofIndirection.com. If you don't remember that, I've also got extra levelofIndirection.com that redirects there. And also another levelofIndirection.com, and even too many levels of indirection.com. Maybe that went too far. And then, well, you can get the rest. So, any questions? You've had a few, so we'll start here. Sorry, is there a... Oh, that's a very good question about boost outcome. Is there room left for something like boost outcome with this? Well, ideally, no. In a way, this is putting something like boost outcome into the language. But the flip side to that is we won't get this for a while. In the meantime, boost outcome is probably the closest we can get in a library. So if you like this, try boost outcome. Good question. And, sorry. Yeah. Does it break compatibility?
Yeah, if I'm using Trycatch today, it's really in a different meaning, right?
So it doesn't break compatibility because if you're writing new code that throws things in a different way, you're going to catch it in a different way. You would have to have done that anyway. But there is an interoperability feature because I mentioned that stood error could hold an exception pointer. So if you're in a function that calls something that throws a static exception, but you're only handling dynamic exceptions, it will convert it to an exception pointer. And vice versa. If you're in a throws function, you call something that throws a dynamic exception, it can convert it to an error code. Stood error. But also you can catch both types in a single set of catch blocks. So either way, there is an interoperability story. But hopefully that's just transitional as we move more things over. Yeah. Yeah. Sorry? Oh, when will it be? Well, it's currently targeting C++ 23, but that's not a given either. So we may be waiting for it for a while, which is why I say, boost outcome may give us something sooner. Some of these things, like stood error, that also may come sooner. Not in 20, we're too late for that. And I don't think stood expected is even coming in 20. I think that's missed that boat. So yeah, we're looking forward a bit, but we'll get there. Was there one up here? Sorry, struggling to hear you a bit. So you're saying about how you apply the try keyword. Mm-hmm. Yeah. So you're talking about the interaction between const expr code and the propagation of errors using std error code. I don't remember anything in the current proposal that specifically talks about that, but it wouldn't surprise me because this hadn't actually gone to the committee yet. Well, they've seen it, but they haven't discussed it. Wouldn't surprise me if that comes up, and we make sure that you can throw things from const expr functions, and that all still happens at compile time. It should do, because if it's the same as returning it as a return code, that should work the same way. But I think that probably needs to be specifically discussed. Good question. At the back.
So will the standard library have to be rewritten in terms of these new exceptions?
Sorry, could you repeat that?
I asked about the standard library. Will it have to be rewritten?
Will the standard library have to be rewritten? I hope it doesn't have to be rewritten, but I mentioned a few things like the changes to contracts, or towards contracts, and potentially changing the bad alloc. Actually, the bad alloc thing won't change much, but the move to contracts, that will involve changing the definition of the standard library. And that's separate from this anyway. It's more of an enabler. And that has actually been discussed in the committee, at least. The room's sort of temperature has been gauged towards that idea, and the library groups were very welcoming towards it. So that may well happen regardless of what happens with static exceptions. There's an idea that, we should be doing more things as contracts. Once we have contracts that everyone's happy with, which doesn't seem to be a given these days, but assuming we get there, we should move things to contracts, and that will change the standard library. In terms of what's left that still throws exceptions, like vector get, I don't know whether we'll change that or not, or whether we'll just add different functions. I think that's still an open question, but potentially, yeah. Okay, and here again.
Did you work on combining both the async and the executor proposals with
Didn't catch all of that, but I think you're talking about the async implications of this, because we discussed that earlier. It's definitely being discussed, but I don't think it's specifically called out in the proposal as it currently stands. And so, as I said privately earlier, I think that's probably something that's going to come up during review, and hopefully we'll get it addressed. And in fact, that's exactly why Swift has introduced the result type, even though it already has something like static exceptions, so that you can keep hold of the result, store it across async boundaries, and a few other cases like that. So we just need to explicitly design that in, but it should enable it quite nicely, in theory. Thanks. So I think that's time. If you've got any more questions, you know where to find me. Thank you very much again.